Hey guys, welcome to Half-Life Practice Problems. So today what we're going to look at is half-lives and just how long it takes for samples to decay and just how much radiation is given off. So that's kind of the key points with half-lives. Some pieces to just keep track of is the starting stuff, the stuff that remains, the amount of time that has passed, and what specific half-life is for that radioactive substance. Before a substance starts to decay, before an unstable radioactive substance decays, we have 100% of that sample. And then after one half-life, we're left with half of those samples become daughter atoms, half of them are still radioactive and still need to decay. So another half-life passes, and then again, half of that substance decays. So keeping that in mind, if we had a substance like bromine 84, just a random one that's not on the, it is on the slide, had a half-life of 32 minutes, and if you started off with 12 grams of that substance, how much would you have after 32 minutes? Okay, half-life, half the sample decays, so we're going to be left with, that's right, 6 grams. That doesn't look like a 6. After another 32 minutes passes, half of the sample is going to decay, and half of it's going to remain. So we're going to be left with 3 grams. Oh, 3 grams. And then if another 32 minutes passes, half of it would decay. So we'd be left with 1.5 grams that would remain. So we're going to try to put this stuff into practice. Looking at problem number 1. What is the half-life of a 100-gram sample of nitrogen-16 that decays to 12.5 grams in 21.6 seconds? All right, let's go ahead and label some of this stuff up. We got 100 grams. We got decaying to 12.5 grams, and this is all happening in 21.6 seconds. So this first number is our starting number, right? So that's the starting amount. The 12.5 is what remains. And then this all happens in 21.6 seconds. So that's the time that has passed. We are starting with 100 grams, and we're trying to figure out, let's go ahead and box what we're looking for. We're trying to figure out the half-life for nitrogen-16. So we're starting off with 100 grams. One half-life passes. So after one half-life, we're left with 50 grams. Is that the same number as 12.5? No, it's not. We got to keep going. So it's got to go through another half-life. So we're going to go through a second half-life. And we are now at 25 grams. We're just cutting 50 in half. Is that 12.5? No, it's not. All right. So we're going to go through a third half-life. If we take 25 divided by 2, cutting that in half is 12.5. Is that the same as 12.5? It is. All right, cool. So we've gone through 3 half-lives. The total time this has all happened, going from 100 grams decaying to 12.5, is a total time of 21.6 seconds. We want to know the specific half-life for nitrogen-16. So we've gone through 3 half-lives. The total time that took was 21.6 seconds. So to find what each, or like how long is each half-life, we're just going to take 21.6 seconds, our total time, divided by how many half-lives that passed, 3 of them, and we'll label this HL, just for half-lives, and not seconds. All right, so we're going to take 21.6 divided by 3, and we're going to get 7.2 seconds. So my half-life for nitrogen-16 is 7.26 seconds. 7.2 seconds. All right, let's try a second one. So let's go ahead and jump over to example number 2. So example number 2, chromium-48 has a short half-life of 21.6 hours. How long will it take 360 grams of chromium-48 to decay to 11.25 grams? All right, let's go ahead and underline up our numbers here. We got that, we got that, we got that. And what we're looking for is how long. How long is this thing going to take? So we don't have our total time, right? In the last problem we did, this time we're looking for how long this is going to take. We are given the half-life though. So we are given what the half-life is, and we're also given our starting amount, starting and ending, and what remains. All right, cool. So we're starting off with 360 grams, 360 grams, and we're just trying to get to 11.25 grams. So after one half-life, so again, after one, we're gonna take 360 divided by 2, cut it in half. We're left with 180 grams. That's pretty far from 11.25, so we gotta go through a second half-life. Cutting in half, we're left with 90 grams. Got ahead of myself. That's not 11.25, we gotta keep going. 45 grams. Oh, gotta go through another one. Let's go through another fourth half-life. So 45 divided by 2, 22.5 grams. That's still not there, so we gotta go through a fifth half-life. And that is gonna be our 11.25 grams, right? So it took 5 half-lives to go from 360 grams to decay down to 11.25 grams. So during that time, that's when it was emitting that radiation as it was decaying. So we're trying to figure out how long the total time is. It says that each half-life is 21.6 hours. So what that means is each half-life here is 21.6 hours. So to go from this to this, that's 21.6 hours. To go from this to this, that's 21.6 hours. And then so forth. From the next one to the next one, that's also going to be 21.6 hours, right? So we just want to find the total time of that. So we could just add up all those 21.6s. Also, we can kind of think it through. Let's switch back to blue. So how long is it going to take, right? So if we go through 5 half-lives and we have a total, and each half-life is 21.6, we want to find out the total time. We can take 21.6 hours times 5 half-lives. All right, so 21.6 times 5, plug that in your calculator. We should get 108 hours. So our total time will be 108 hours to go from 360 grams to decay down to 11.25 grams. All right, so we've gone through half-life problems. There are different ways to process this. One is just kind of thinking it through, and there's different ways to think it through. Whatever works for you is what I would do. There are equations you can use too. So if you like that type of stuff, so I'm going to jot something down here. So this T half is usually what represents a half-life. So the half-lives that pass or elapsed, so the amount of half-lives that you go through is equal to the total time that has gone by divided by the half-life, or the specific half-life for that nuclide. So this is an equation that you could try to use if you want to solve for it, but otherwise I would just process it through. If I wanted to use this equation for this type of problem, or this specific problem here, our total time was our x. We didn't know what our total time is. We knew our specific half-life was 21.6 hours. And then we saw that we went through 1, 2, 3, 4, 5 half-lives. So we could solve for x, which is still going to give us 108. And then the unit for that is going to be hours. All right, so we're going to go ahead and try 3 problems, or y'all are going to try that. So go ahead and pause the video, guys, and try those 3 practice problems, and then I'll toss those answers up. So pause. All right, 1 half-life has gone back. No, that was lame. Let's go ahead and toss these answers up here. So for number 1, hopefully you got 15 hours. Number 2, hopefully you got 24.3 days. Number 3, hopefully you got 26.5 grams. All right, cool. So check your work. Make sure you got one of those 3 numbers, or not one of those 3 numbers, all 3 of those numbers. If you didn't, definitely rewind, rewatch stuff, see where you went wrong, and just double check your work. All right. Before we go, one more thing I kind of want to touch upon, giving you a little bit of dating advice. No dating advice here. Radiocarbon dating. So if you ever imagine yourself being an archaeologist and you were dating stuff, in terms of like figuring out how old stuff was, that's what radiocarbon dating is. So we are absorbing carbon-14 as we speak. So living artifacts, living substances take in carbon-14, and when we die, carbon-14 starts to decay. We've seen that before, right? So remember, this is our beta particle. So carbon-14 goes through a beta decay. And based on how much carbon-14 is decaying, we can try to figure out approximately how old something is. So last problem I want you guys to try is trying to use that carbon dating in a problem. So take a look at this problem. You find a woolly mammoth in your backyard, because that's for sure can happen. And radiocarbon dating shows that it has only 25% of the carbon-14 expected in a living mammoth. How old is your mammoth? If you need a hint, the start of it, you have 100% of carbon-14 until it dies. And then the half-life of carbon-14 is 5,730 years. So try that. All right, cool. So hopefully you got 11,460 years. If you didn't get that, definitely retry it, but think it through. You start off with 100%. How many half-lives is going to get to? How many half-lives is going to take to get to 25%? And then each half-life is 5,730 years. All right, cool. Go watch Ice Age.